Next, let's discuss the question that how to get the quality factor from the frequency characteristic. In the general resonant frequency characteristic, we can find two half power points. 0.707 corresponds to negative 3 dB. It's a half power point. We've introduced this in lecture 70. We are interested in the fact that the magnitude frequency characteristic can be regarded as a bandpass filter. It has two intersections with 0.707. Signals within the frequency between the 2 points can pass, and signals with other frequencies are all attenuated. So we should solve the value eta of the 2 points. They are defined as eta 1 and eta 2 respectively. In general, resonant frequency characteristic, its value is defined as 1 over the root square of 2. Q is supposed as an underdetermined coefficient, so this is a quadratic equation of eta. We can easily solve two roots of the equation. Their expressions are a little complicated, but it doesn't matter. The frequency which we are interested in is here. We can get a simple expression eta 2 minus eta 1 equals 1 over q. Now we get the third definition of the quality factor. Quality factor is defined as the reciprocal of the difference between the two half power points. Eta is a relative frequency, but we often use absolute frequency in the actual frequency characteristic. So eta is substituted back by omega over omega 0. Then we get the expression of omega. Omega 0 is resonant angular frequency. Omega 2 and omega 1 are two half power points in general resonant frequency characteristic. Of course, omega can be transformed into the form of f in the expression. Omega 2 minus omega 1 or f2 minus f1 is called the bandwidth. BW is short for bandwidth. Signals with frequency within this range can pass. The width of this frequency range represents the performance of the bandpass filter. According to this expression, we can easily solve the quality factor of a resonant circuit from the frequency characteristic. About this, we look at a simulation. We use this circuit to explain how to measure the quality factor from the frequency characteristic. You see, this is a serial circuit consisting of 1 ohm resistor, 1 microfarad capacitor, and a 1 millihenry inductor. We can easily solve its resonant frequency is 5.035 kHz. The quality factor is 31.6. Now we draw the frequency characteristic of the current. Because we've calculated the resonant frequency, so we set the frequency range as from 4.8 K to 5.3 K. The output is the capacitor's current. We delete the phase characteristic. In the magnitude characteristic, we should verify whether the resonant frequency is 5.035 kHz, the same as the theoretical analysis. We move the cursor. When the frequency is 5.0333 kHz, the vertical axis is 999 milli, and the characteristic reaches its maximum value. This is accorded with the theoretical analysis. Now we use the cursors to find the two half power points. You see, the frequency difference between the two cursors is 159. According to the previous theoretical analysis, the quality factor of the circuit is 31.6.